Picture this. You're getting ready to give a big presentation in front of, like, a lot of important people. You're practicing in front of your mirror, and then, just for a second, you forget how to speak. Suddenly you feel that familiar sting of anxiety, like an icy hand on the back of your neck. You look at yourself in that mirror, and you start imagining some of the worst case scenarios. Like, what if you totally lose your train of thought up there? What if you barf? What if everybody gets up and leaves? Now you're really nervous. I'm getting freaked out just talking about it. So you start taking quick, shallow breaths, and you're feeling lightheaded and seeing stars, and now you, my friend, are hyperventilating. When we talk about respiration, we tend to focus on oxygen, and who could blame us? It's easy to forget the equally important role that carbon dioxide plays in maintaining homeostasis. Your internal balance between oxygen and carbon dioxide factors heavily into all sorts of stuff, especially in your blood, where it can affect your blood's pressure, its pH level, even its temperature. And now, at like T-minus 5 minutes to your presentation, all those things are out of whack because you're exhaling more CO2 than you should. You're just about to faint when a friend suddenly hands you a paper bag to breathe into, and you've never been so grateful for a lunch bag in your life because somehow it does the trick. Within seconds, you're back to normal. The drop in CO2 that occurs in your blood when you hyperventilate is called hypocapnia, and it signals a breakdown in one of the most complex and important functions that your respiratory system performs. That is, the exchange of gases inside your blood cells, where the stuff your body doesn't want is swapped out for what it desperately needs. This exchange between carbon dioxide and oxygen is regulated by a whole series of biological signals that your blood cells use to communicate with your tissues about what they have, what they want, and what they need to get rid of. It's almost like a code, one that's written into your blood's chemistry, in the folding of its proteins, even in its temperature and acidity. It's what allows you to perform strenuous physical tasks like climbing a mountain. It's also what lets you reboot your whole respiratory system with nothing more than a paper bag. I'll admit it, when we've talked about the chemistry of your blood so far, we've tended to keep things pretty simple. Like hemoglobin contains 4 protein chains, each of which contains an iron atom. Since iron readily binds with oxygen, that's how hemoglobin transports oxygen around your body. Bada bing! But the fact is, hemoglobin's affinity for oxygen isn't always the same. In some places, we want our hemoglobin to have a high affinity for oxygen so it can easily grab it out of the air, and in others, we want it to have a low affinity for oxygen so it can dump those molecules to feed our cells. So how does your hemoglobin know when to collect its precious cargo and when to let it go? Well, a lot of it has to do with a principle of chemistry known as partial pressure. One of the things that fluids always do is move from areas of high pressure to low pressure. And molecules also diffuse from areas of high concentration to areas of low concentration. But when we talk about gases in a mixture, we need to combine the ideas of pressure and concentration. See, air is a mixture of molecules, and when you're studying the respiratory system, you often need to focus on the oxygen, which makes up about 21% of it. But that doesn't actually tell us how many oxygen molecules there are. For that, we need to know the overall air pressure, since more molecules in a certain volume means more pressure. So partial pressure gives us a way of understanding how much oxygen there is based on the pressure that it's creating. Example. The pressure of air at sea level is about 760 millimeters of mercury, but since only about 21% of that air is oxygen, oxygen's part of that pressure, or partial pressure of oxygen, is 21% of 760, or about 160 millimeters of mercury. Now, that's just outside at sea level. When that air mixes with the air deep in your lungs, including a lot of air that you haven't exhaled yet, the partial pressure of oxygen drops to about 104 millimeters of mercury. And in the blood that's entering your lungs after most of its oxygen has been stripped away by your hungry muscles and neurons, the oxygen partial pressure is only about 40 millimeters. This big difference in pressure makes it easy for oxygen molecules to travel from the outside air into your blood plasma because, as a rule, dissolved gases always diffuse down their partial pressure gradients. This is why it's so much harder to breathe at higher altitudes. When you climb a mountain, the concentration of oxygen stays at about 21%, but the pressure gets lower, which means the partial pressure of oxygen also decreases to about 45 millimeters of mercury at the top of Mount Everest. So the partial pressure of oxygen at the top of the highest peak in the world is almost the same as the deoxygenated blood that's entering your lungs. So basically, there is no partial pressure gradient, which makes it really hard to get oxygen into your blood. But let's get back to the red blood cells. Remember that the globin in your hemoglobin is a protein, and when proteins bind to stuff, they tend to change shape, and that shape change can make the protein more or less likely to bind to other stuff. When an empty hemoglobin runs into an oxygen molecule, things are a little awkward. It's like a first date. Bonding isn't so easy. But once they finally bind, hemoglobin suddenly changes shape, which makes it easier for other oxygen molecules to attach, like friends gathering around the lunch table. That affinity for joining in, or cooperativity as it's known, continues until all 4 binding sites are taken and the molecule is fully saturated. Now your hemoglobin is known as oxyhemoglobin, or HBO2, and it is not why the cable network is called that. That's the home box office. Anyway, by the time the blood leaves the lungs, each hemoglobin is fully saturated. The oxygen partial pressure in your plasma is about 100 millimeters, and now it is ready to be delivered to where it is needed most. Active tissues like the brain, heart, and muscles are always hungry for oxygen. They burn through it quickly, lowering the oxygen partial pressure around them to about 40 millimeters. So when the blood arrives on the scene, oxygen moves down the gradient from the plasma to the tissues to feed those hungry cells. That makes the oxygen partial pressure in your plasma drop, so your hemoglobin starts to give up more of its oxygen to the plasma. But partial pressures are only part of what's prodding your hemoglobin to give up the goods. All of that metabolic activity going on in your tissues is also producing other triggers in the form of waste products, specifically heat and CO2. Both of those things activate the release of more oxygen by lowering hemoglobin's affinity for it. Say you're climbing that mountain again and your thighs are feeling the burn. Red blood cells saturated with oxygen are going to the muscle tissue in your quads, where the hemoglobin can dump a bunch of O2 because of the lower partial pressures of oxygen in your muscles. But a hard-working quad will also heat up the surrounding tissues, and that rise in temperature changes the shape of hemoglobin, and it does it in such a way that it lowers its affinity for O2. So when those red blood cells hit that warm, active tissue, they release even more oxygen, like 20% more beyond what partial pressures would trigger. But wait! There's more! Carbon dioxide triggers the release of oxygen too, because it also binds to the hemoglobin, changing its shape again, lowering its affinity for oxygen still more. And as oxygen jumps ship, the hemoglobin can pick up more CO2. Finally, just in case the hemoglobin isn't getting the message at this point, there's one more trigger that your respiratory system has up its sleeve. The spike in CO2 that's released by your active muscle tissues actually makes your blood more acidic. Since your blood is mostly water, when CO2 dissolves in it, it forms carbonic acid, which breaks down into bicarbonate and hydrogen ions. Those ions bind to the hemoglobin, changing its shape yet again, further lowering its affinity for oxygen. So now, at last, your tissues have the oxygen they need, and your red blood cells are stuck with all this CO2 that they need to get rid of. Your red blood cells ride the vein train back to the lungs, where they encounter a new wave of freshly inhaled oxygen. And when that O2 binds to the hemoglobin, which again is hard at first, it eventually changes its shape back to the way it was when we started, which decreases its affinity for CO2. So the hemoglobin drops its carbon dioxide, which moves down its partial pressure gradient into the air of your lungs, so you can exhale it and the whole thing can start all over again. Now, if that isn't enough to make you hyperventilate, I'm not sure what is. But this brings us back to that unfortunate episode you had before your big presentation. This whole complex code of chemical signals that I just described, well, it assumes that what your cells and tissues are telling each other is actually true. But as we all know, sometimes our bodies don't mean what they say. Thanks, buddy. Like when you're freaking out about your presentation, your sympathetic nervous system makes your heart race and your breathing increase to prepare you to fight or flee. The problem is, there's nothing to actually fight or flee from, so your muscles aren't actually doing anything, so they're not using all the extra oxygen you're breathing in. And they also aren't producing the extra CO2 that you're suddenly exhaling all over the place. So when you start to exhale CO2 faster than your cells release it, its concentration in your blood drops. And with less carbonic acid around, your blood's pH starts to rise. And you know what else? Well, low blood pH does things like change the shape of your hemoglobin to deliver oxygen. High pH causes vasoconstriction. Normally this is supposed to divert blood from the parts you're not using during times of stress, like your digestive organs, to the parts that you are using. But when you hyperventilate, this constriction happens everywhere, which means less blood is delivered to your brain, which makes you lightheaded. Luckily, that trick with the breathing into the paper bag, it really does work. It works because it lets you breathe back in all of the CO2 you just breathed out. So the partial pressure of carbon dioxide in the bag is higher, which forces that CO2 into your blood, which lowers its pH, and you get back to homeostasis. And of course, homeostasis is the key to life. And also to a successful presentation. If you were able to remain calm today, you learned how your blood cells exchange oxygen and CO2 to maintain homeostasis. We talked about partial pressure gradients and how they, along with changes in blood temperature, acidity, and CO2 concentrations, change how hemoglobin binds to gases in your blood. And you learned how the thing everything with the bag works. Of course, we must say thank you to our patrons on Patreon who help make Crash Course possible through their monthly contributions, not just for themselves, but for everyone. If you like Crash Course and want to help us keep making videos like this one, you can go to patreon.com/crashcourse. This episode was filmed in the Dr. Cheryl C. Kinney Crash Course studio. It was written by Kathleen Yale, the script was edited by Blake T. Pestino, and our consultant is Dr. Brandon Jackson. It was directed and edited by Nicole Sweeney. Our sound designer is Michael Aranda, and the graphics team is Thought Cafe.